It's okay, okay, it's okay. Ok, bueno. Hola, ¿qué tal? ¿Cómo estamos? Buenas tardes. Vamos a dar inicio ya a nuestro seminario del día de hoy. Y bueno, para mí es un gran gusto. It's a very pleasure that Professor Rainer Krull is again here in Mexico. Since, what is the year? 2011. 2011. So, and I'm going to make the introduction from the professor, but I'm going to use the Spanish, please. El profesor Rainer Krull, que ha estado aquí ya con nosotros desde en el 2011, actualmente es director académico en el Instituto de Ingeniería Bioquímica en la, I'm going to make the translation, Universidad Técnica of Braunschweig.
My PhD.
No, but about the position now.
Yeah, in Braunschweig.
So, él es, actualmente también coordinador del programa de intercambio de estudiantes de esta universidad con estudiantes de la Universidad de Waterloo en Ontario. También, bueno, él es coordinador del programa europeo Marie Curie para temas de innovación, sobre todo enfocados hacia aplicaciones de microbioreactores y procesamiento o bioprocesamiento. Los temas de interés del profesor Rainer Krull están enfocados hacia el desarrollo de bioprocesos, ingeniería y morfología, principalmente en organismos filamentosos, esfuerzo al corte de microorganismos, desarrollo de microbioreactores y procesos biotecnológicos. Esto he tratado de ser lo más breve posible. Evidentemente el currículum del profesor Rainer Krull es realmente muy extenso. Para mí es un gran gusto que esté nuevamente aquí. Thank you very much for again stay here in Mexico. Y bueno, les recuerdo, además del seminario que nos va a dar hoy el profesor Krull, Él va a participar, nos va a dar un curso sobre microreactores y organismos filamentosos. Ya hay varios estudiantes que me mandaron un correo para confirmarme su asistencia. Empezamos hoy a las 4 de la tarde aquí en el auditorio. Todavía tenemos espacio, yo creo que unos 5 espacios, algo así, Clau, 5 espacios para aquellos que estén interesados, que quieran anotarse. Por favor, mándenme correo a mí o a Claudia Aguirre para que podamos registrarlos en el curso. Y pues nada, empezamos con el seminario. Thank you very much, Rainer.
Okay.
Would you prefer, but it's
okay. It's okay. Leobardo, hello.
So, is this good for you or maybe down?
I think it's good for to stand here. Thank you very much, Carlos, for the nice introduction, and welcome here to the seminario from the Institute. And I'm very happy to be here to help also the lectures about filamentous microorganisms and microbioreactors. So we decided to make this main lecture for the introduction of new microbioreactors in the field, which we are, since 15 years we are working in this, and I will give you an introduction to that. So microbioreactors for process development and cell-based screening studies. But before I want to start, I want to make a little bit, I would go into the history of our history here with Cuernavaca and Braunschweig. I met Enrique Galindo in 2009 at the Montreal World Chemical Engineering Conference, and there the chairman was Agirius Margaritis from the Western Ontario University in London. And we make the Montreal Protocol, so we visited each other. Agirius was here in 2011, and the group of Agirius Margaritis and Enrico, we were in Braunschweig. We met in Braunschweig, and then I organized a train tour to Aachen, where Carlos also has his education, his postdoctoral education, and we were here at the main hall with Jochen Büchs and Agirius Margaritis. In March 24, I was here in Cuernavaca, here in excursion with Enrique in Tepoztlán. In 2012, there was PhD students, a student Thomas Wucherpfennig here. We make a paper with Gabriel Corchidi for the image analysis of Taxus chinensis plant cells. 2011, on the ECAP conference in Berlin, Carlos and his wife and also Tanya made a stopover when they went to Aachen in Braunschweig for 2 days. And in 2022, there was Jana Niebusch here as a PhD exchange student in your group to work in the field of biopolymers. So, and when I make my lectures about steering, then I present this paper from the group of Gabriel and from Enrique, the characterization of the molinillo. It's a steerer, and there I give the student the manuscript of this publication, and this is a nice example to make with the right geometry, with the right Reynolds numbers, with the right power numbers, the most foam of cacao. This is a nice example for that. So hopefully Gabriel and Enrique are not still here, but hopefully I will meet them. Okay, let's start the first slide in the microbioreactor. So I start with this slide. On the left side, the biggest bioreactor I know from literature, it's the Billingham airlift loop reactor for the production of single cell proteins in September 78 with 2,300 cubic meters. It was not an economical subject. They finished the production after 1.5 years because it was not economically. So on the left-hand side, on the right-hand side, I show you a microbioreactor with only 50 microliter, and we want to Yeah, it's working, but I doesn't see nothing here. Okay, but this is 50 microliter, and we want to measure optical density, pH, dissolved oxygen, also glucose concentration in such small devices. And mostly the big advantage is that we have a parallelization of these reactors. Literature. There are 2 books. There is a comprehensive state-of-art reviews. The first book is Microsystems for Pharmacotechnology, Manipulation of Fluids, Particle Droplets and Cells, edited by Andreas Dietzel from the Microtechnological Institute in Braunschweig. And the second one, a new one in 2022 of Alexander Grünberger. He is now a new professor in Karlsruhe Institute. And Janina Bahnemann, she is now in Augsburg, and they make microfluidics in biotechnology, and these are very nice reviews about the microbioreactor subject. So we are talking about microbioreactors when we have still under 1 milliliter scale. 1 milliliter scale, 1000 microliter, this is called microbioreactors. In the nanoliter, picoliter, femtoliter scale, we are called this is microfluidic single cell bioreactors. This is the subject which Alexander Grünberger worked in. So the advantages is in media and sample saving. We have good process informations about optical sensors, so you can't take a manual probe of this little microbioreactor, so all these sensors are optical sensors. Then you have a high degree of automation and a high degree of parallelization. They replace increasingly shake flasks, so you have a higher cultivation throughput combined with enhanced cost efficiency. And then we have here, as example, the amber systems of Sartorius, or you have the micro-titer plates from, oh yes.
Maybe this is better,
yeah,
but it's only used from the laser, but not to change the light.
I change it. Thank you.
But you can change. Okay, it's possible to change this.
Okay. Yeah, it's okay. Mm-hmm. There are also these micro-titer plates from M2P labs, or this flow-through plug flow reactors. These increasingly replace these shake flasks. So this amber system is most commonly used for mammalian cell culture cultivation. The main applications are high throughput screening, cell-based assays and cell analysis, I will talk about later, and also screening and bioprocess development. So here's an overview of the literature in microbioreactors and the microfluidic single cell bioreactors. In gray, we have developments in material. It started in the beginning of 1990s with the most common term, micro total analysis systems, MicroTAS. Also a conference is MicroTAS conference now in this year in Montreal. And it was developed by the group in Saarbrücken from Manz. And they used this log systems in the instrumental analytics, so in the chemistry, in the capillary electrophoresis. And then also the term microfluidic is founded by Graversen 93. Then there are the development of suitable polymers materials like polydimethylsiloxane or PMMA. and also the use of photosensitive glasses like shot glass from mines, from the Futuran glass. So these are mostly the developments in the material. Then on the microbioreactor scale, the first reactors are developed in the miniaturized scale reactors, milliliter scale, by Puskeiler and also by Bett and Bagans from the UCL in London. And the first reactors down to the microliter scale is from the Jensen group at MIT in 20 years ago, from Sansotto and Zhang, and also the colleagues of Nicolas Zita and Gerardo Pierocello were in the game at that time at the MIT. Then also the group of Chris Gurney at the DTU and also Braunschweig group started the first microbioreactors in the 2010, and then we are working together in this European community program and the Marie Curie program, and develop several other examples like the capillary wave microbioreactor, which I will present here in the lecture. On the other side, down to the picoliter scale, we have droplet microfluidics at the end of the 90s, and also the single cell growth channels, and also advanced single cell cultivation setups by the groups of the Jülich group and also the Grünberger group now in Bielefeld and also in Karlsruhe. So what are the main comparisons when we are discussing these microbioreactors? So the comparison is by different mixing types, by stirring, by pumping, by pneumatic gassing, orbital shaking, or by the vertical shaking when we have capillary waves of sessile drops. And in the next slides, I have the plus for advantages and minus for disadvantages. First, the mixing via stirring. Here we have an example of the Zhang group and also from the Chris Gurney group from Scheper et al. And here we have stirrers, but a big disadvantage is to have stirrers in such micro devices. It's not a good idea to have this. So it's a good approach for scaling and mechanical stress in stirred tank reactors, but several disadvantages like moving parts in a small volume, accumulation of carbon dioxide bubbles, cell respiration, degassing is disturbed, and oxygen is negatively affected. Mixing via pumping, also two examples. No moving elements inside reactor chamber, very gentle homogenization, so advantage for mammalian cell culture analysis, but also we have low oxygen transfer. It's not so a big part in the cell culture cultivation, but mostly you have only a surface aeration in these reactors. So we have learned that we have carbon dioxide accumulation, so we make a vertical positioning to a bubble column reactor. We did that in the last years. We have a bubble column reactor with 150 microliter, also a little bit higher volume with pH, oxygen, and glucose. And also we developed a 3D printed bubble column reactor with a 500 microliter volume. So no moving parts, improved oxygen transfer by active gassing, and also a degassing of a stripping of carbon dioxide by vertical arrangements, a better increase in back mixing for nutrients and cells, but when you use mammalian cells, you have a high mechanical shear stress when you use these reactors. So then we came to orbital shaking. Also Funke, mostly here from the group of Jochen. It's orbital shaking, mostly used for microtiter plates formats, but smaller fluids volumes down to 50 microliter are difficult to mix because you have larger surface forces seen in smaller volumes. You have to bring more power into the game to extend these forces. And you have to overcome also the surface tension because you have a high area to volume ratio. Mixing by capillary waves. So this reactor has a volume of around 10 microliters. So it's an open cavity, and here it's in photoran glass, and you have here low mass transfer oxygen, the surface aeration, and when you bring this in a vertical oscillation, you bring this reactor on a loudspeaker with defined frequency and defined oscillarity, then you get a good oxygen transfer on this little volumes. So no moving parts. Oxygen transfer can be tailored by oscillate frequency and amplitude. Even microorganisms with a high oxygen uptake rate can be cultivated without oxygen limitation and high biomass concentration, increased backmixing, degassing, and also mixing down to 5 microliters are available. But a big disadvantage due to the open cultivation system, you have to work against evaporation as an inherent challenge. And we solved it, hopefully, with this kind of example, which I show you afterwards. So the first developments are these horizontal microbioreactors. The bottom is glass, and then on this glass material you have a PDMS lid. This PDMS lid, it's oxygen permeable, and it's like a surface aeration. No active aeration, and the sensors here are the optical density and also dissolved oxygen online. So there are two companies, they make this, it's Presense and also Pyroscience. Pyroscience also in the near of Aachen, and Presense is in Regensburg in Germany. So they developed all these online dissolved oxygen sensors. We did the first cultivations with Saccharomyces cerevisiae in a chemostat cultivation and make also kinetic analysis. But there are still also limitations. PDMS is a hydrophobic surface. You have a strong cell adhesion and you have a development of biofilms that you don't want to have. You want to have a planktonic growth of the microorganisms, and you have no real good backmixing, and the oxygen transfer is limited, and you have also the accumulation of carbon dioxide bubbles. So we have to make a surface technology so that the PDMS is more hydrophilic, and so we use the bubble column systems here. We're still in the laminar flow. Reynolds number is defined as a characteristic length, a velocity, and the kinematic viscosity nu. We have also no moving parts, and we have several advantages: improved oxygen transfer by active gassing and degassing by the vertical arrangement. Here at the bottom we have a a gas parger with a diameter of 30 micrometers. And we have, by the hydrophilization of the PDMS, a very good homogeneous bubble spectrum over the cross-sectional area. So we are working with the Institute of Microtechnology in Braunschweig. They designed, constructed, and manufactured these reactor systems. So the construction is PDMS on glass. This is a first construction. They make like this, it's copy. Then on this here we have the PDMS lid, and afterwards we bonded this by plasma activation on the glass surface. So we have a cheap, biocompatible, transparent, gas permeable, and hydrophobic material. And this is a disadvantage when you are making your cultivation. You have a coalescence of the bubbles in the reactor system, and you can't make such a cultivation. And so we make the hydrophilization of the PDMS surface by a flow-through device, and we used PEM multi-layers on these microsystems. And on these flexible interlayers, we make a pegylation here, so we have several slices here with a high peg density, and this makes the surface more hydrophilic. So that we have here with a superficial gas, with increasing superficial gas velocity, a very good homogeneous bubble aeration. With that, microreactors is not every time micro and small. You have very much apparatus setups in the game. Here's the reactor system. We measure the dissolved oxygen here with a micro needle from Unisense or from Presense. Then we have an optical density fiber optics here. We measure, we stop the aeration, and then we are measuring the optical density here in this direction. Then we have a sampling in the first years. We have a sampling by HPLC, glucose and ethanol. Okay, and we have volume rates between 0.5 to 100 milliliter per hour. It's not very much. And with that, we make a batch cultivation here, exponential optical biomass growth, and without oxygen limitations. We can measure the specific growth rate and the yield coefficients. And then after that, we make a continuous cultivation of Saccharomyces cerevisiae, like a hemostat experiment at different stationary values. We measured these stationary values for glucose, ethanol, because it's a Crabtree positive yeast. And with that, we can make also modeling, and we have also the comparison between the literature in the lab scale and also with our bioreactor column here. And the first, you have a production of biomass, and over 100 milligram per liter in the reactor of glucose. Then you have the Crabtree effect. You compensate, the biomass is decreasing, and the ethanol product is increasing over the dilution rate here. And here at the washout, you have at every product, biomass and substrate concentration, you have the limitations here at the end. So, but it's a good model. We can look here at the literature and you can use these microbioreactors to make a good kinetic analysis. Then the next reactor is purely in glass, fabricated in glass by the microtechnology company, also with this part at the bottom with 30 micrometers. This is a big issue here. Also here you see a very good bubble, homogeneous bubble over the reactor. And then we make the first characterizations. Here the KLR value with the dynamic gassing out methods over KLA values with this reactor up to 320 per hour. Also mixing time experiments. So we get older and older, we have not so much good eyes. So you have this on a video, this reactor, and make photos for these mixing time experiments with the fluorescein dye. And also with Ulrich Grüne at the DTU in Denmark, we make transient modeling, CFD modeling, to see the mixing of this microbioreactor down to 5.5 seconds here at higher superficial gas velocities. The next one, we included also a glucose sensor in the reactor. We have the dissolved oxygen over the cultivation. We have the scattered light for biomass concentration, cell dry weight concentration. We have the oxygen uptake rate here, and we have the glucose concentration over the cultivation time. I will look for here is a glucose sensor. This glucose sensor is out of two sensors. Here we have the oxygen sensor with oxygen-sensitive particles. On the other side, we have the glucooxidase also in the inner shell over a diffusion barrier, and from the constant oxygen concentration and the decreasing oxygen concentration, you have a delta, and from this is proportional, this is correlated with the glucose concentration in the cultivation broth. I will go back. So next generation is the 3D printed microbubble column reactor. So we have several 3D printed parts here, and here in this part we have also, in this glass slide, we have optical sensors for optical density, for pH, for dissolved oxygen inside. Optical fiber spectrometer, mass flow controller are inside, an optical chemical sensor spot for dissolved and pH, temperature control, and also exhausted gas for carbon dioxide in the off gas. The other reactor is the capillary wave microbioreactor, a cavity of 7 microliter. It's produced on a wafer with several 25 microbioreactors manufactured by means of femtosecond laser technology from shot photoran glass. And it's high optical transparency and chemical resistance. We put it on here on a loudspeaker, and we measured biomass via light scattering. We have a readout for oxygen and glucose sensors from the Broughton side, and also the mixing by vertical oscillation. In theory, you have such mixing characteristics, and we make also photos at the resonance frequency at 70, 150, 240, and 330 hertz. And it's like the theoretical characteristic. It's also here in the experiments. So when you have the frequency here, and here the volumetric liquid phase oxygen transfer coefficient, KLA, you see at the resonance frequency, you have mostly the best KLA values. And we did this experiment, and we say it like the in-phase and out-of-phase experiments from Jochen with viscosimetry and also with biopolymers. We say we have an experiment out of resonance, here at this or that frequencies, and we have one in resonance. And in resonance you have the big advantage that you have a nice biomass growth for Escherichia coli and varying oscillating settings. We did also triplicates for that, so that we can see at the resonance frequency we had the best characteristics for our proof of concept for E. coli cultivations. And also we can tailor the KLI value from low to high values, from 68 to 275 per hours, and you see also a better growth at the better resonance frequencies as at lower ones. So then we embedded this capillary wave microbioreactors in a 3D printed mounting with moistened sponges, because we have to work against the evaporation, and with this lid and this moistened sponges we minimize the evaporation down to 0.1 microliters per hour. Here you see the sponges, here the holder for the reactors, and inside are the WMBR reactor. So, and here you see this cultivation also with triplicates with E. coli, oscillation frequency about 70 hertz. It's also the first resonance frequency and amplitude, and the KLR around 210 per hour. You have the glucose here, the scattered light, the dissolved oxygen, it's not limited, and the pH value over the cultivation time. So this is the first successful sensor application and a setup for further applications. And we are searching for a new application, and this is the new manuscript from Kevin Febrock in New Biotechnology. We use this as a phago screener, so a novel phagogram platform based on this reactor systems. We are working together with the Fraunhofer Institute in Braunschweig also. They are medical, the item, and the phage therapy is therapy of infection with antimicrobial resistance bacteria by bacteriophages, and these phagograms are sensitive tests of bacteria against different phages for phage therapy, and the big challenge is here that they are very work intensive, not highly parallelized nowadays. So we used our 3-to-3 parallel microbioreactor platform. Then we incubated the model system without phages, then with 2 other phages, and we see following results. Here, the control. And with the phages, we decreased the biomass growth over time very drastically. So it's very nice to see that this platform is reliable for this phagograms in a parallelized style. And then we make an automated platform with 9 microbioreactors with the small volumes. We pipette 2 nanoliters by a dispenser into these reactor systems, and we have a phage repellent hydrophilic surface, and we measured the biomass here in these reactors by an optical density. So we make phage sensitive screens, and also we make these phagograms, which I showed you, over time with different concentration and with different phages. So a nice application for pharmaceutical, medical application field. So I come to my conclusions. The microbioreactor systems allow speeding up the development of bioprocesses, a better understanding of microbial physiology in process conditions, high throughput screening. We have not the 96 or 45 parallelized microtiter plate, but there are several advantages to do this. When you make phagograms, then you have also an adsorption of these phages at the microtiter material. So, and high throughput experimentation at reduced cost for expensive substrate and the ability to investigate large strain libraries. Also, they have reached application status with the mixing type and also with the sensor platforms we used. They ensure a broad range of biological screening application, like analysis of reaction kinetic, pharmacokinetics, and also drug deliveries experiments or medical screenings, like antibio or phagograms. And also, they will improve systems for systematic application in future for scale up or scale down application study. I don't say something about scale up and scale down, but in the lecture I will do make a lecture about this feature also. So this Marie Curie project which was running from 2014 until 2017, it was coordinated by the DTU from Chris Gurney, and we came to several people together, UCL, TU Graz, Ljubljana, Madrid, Braunschweig, ULU, and also DTU. And we decided to make a summer course program, and we did that in this September in Catanzaro in Italy, 2 times in Braunschweig, and we decided to do this at the end of August in 2025. Ulrich Grüne will be the organizer at the DTU. Here are some pictures in Catanzaro, in Granada last year, in Braunschweig in 2018 and 19. We have lab hands-on in sensoring, in cultivation, in microtechnology and so on. So very nice international summer trainings course with around 50 students which are interested in at the end of the master program or in the beginning and at the PhD work. So I have to think you need for research, you need every time fresh money. So you need many thanks to the DFG, the German Research Society, research unit in microsystem and particular life science products in the Marie Curie program, which bring us in the contact with the people from Augsburg, from DTU, Marco Marquez, Thorsten Meyer, Adalma Sesai. She is now at the Harvard Institute, WITS Institute at MIT, and Nicolas Sita from the UCL, and also the PhD students over the last decade, from Astrid Ettlich to Gabor Schulz. He's now they are the current PhD students in the project of the 3D microbioreactor and the capillary wave microbioreactor. And I thank you for your attention, and I'm happy to have a little bit discussion with you. And before we end it, I have to make this announcement. Carlos will do this.
Okay, thank you very much.
Thank you.
Pasamos a las preguntas, dejamos esta transparencia para invitarlos a esta plática de Enrique. Thank you very much, Rainer. So, if there are some questions, aquí con... Permíteme. A ver, ayúdenme. Vamos a prenderlo, ¿sí?
I think this is needed because it's being transmitted online, right?
No.
No, creo que no está. A ver, cámbiame.
No, what I need the microphone because it's transmitted
Ya,
online.
eso es medicina.
Because you can...
I hear you, yeah.
Okay.
Okay, yeah.
Now, okay. Thank you very much, Rainer. So I noticed that your oxygen transfer rates were really relatively high, right? In the order of 300 and higher inverse hours. And I also noticed that the bubbles were very small. So that means they're very fine bubbles. So what I'm worried, and maybe that's why you're getting so high KLAs, but what I'm worried is for many systems, for instance, the ones we use, we work with mammalian cells, the problem of carbon dioxide desorption is important. And when you have that very small volumes, then that becomes a problem. So that would be one. Well, I have a couple other questions, but this is something that concerns the CO2 desorption in the system.
The first, we didn't make mammalian cells until now, only with bacteria. And we have not real foaming in the reactor. And I know from more tiny bubbles that you have problems with that. So these are the micro bubbles and smaller. I know this from, but here in this scale we have no problems with that. With no adsorption or something.
But you use synthetic media, right? So when you go to a more complex media, the foaming...
It's synthetic medium.
There would be a problem with the foam formation. And
so we have no... with complex media or something. So filamentous microorganisms, microbioreactors are contradictionary. So we don't use filamentous bacteria here or complex media here.
I see, okay.
Yeah.
And the other, because it looks great for high throughput screening, but in the pharmaceutical, we usually need to generate enough amount of the recombinant protein to do a whole characterization, so that would be limited unless now you develop the microassay systems, and
so
I
you
think
can do. So we are discussing also how can we make a metabolic flux analysis with that. It's not easy because you need a high concentration of your proteins and so on, and also you need probes of this for this metabolic flux analysis. And this is also a problem with that. Yeah, it's right. So when you make basic fundamentals to make parallelization and process several cultivation experiments, it's a right way to do this. Yeah, but you are staying in concurrent, you are staying in competition with microtiter plates also. And we go with the microtechnologies, we go a scale more down. And we want to create, and Alexander Grünberger with his picoliter scales, he want to develop, investigate more population heterogeneities with this kind of single cell microbioreactors.
I see. At the beginning of your talk, I was wondering about the evaporation, but then you mentioned that with these sponges, that's enough to control because that could be a challenge.
It's
right?
so much work for the PhD, but we scale it down to 0.1 microliter. It's hard to do this, but when you have this open cavity, then you have to do this in this way. It's not we are searching for a better technique to decrease the evaporation rate.
Thank you.
Yes. More questions?
Leobardo.
Thank you, Rainer, for your talk. I'm wondering why your mixing time is quite large, 5 seconds for this volume. I mean, what do you think is the problem? Is more like the assessment of the mixing time, or the device, or the bubble generation? And
I think
what's going on there?
when you see this mixing with the fluorescein dye, you see it's going on the right side down, and then it came into the sparger. So this is where you put this dye into the reactor. When you put it at the bottom directly at the sparger, you are more fast. It's
faster homogenization of the cultivation. And the other question is, of course, this is a valuable system for when you want to make a strain screening or media. But what about the high density cultures? I mean, because we are interested, for instance, in terms of quorum sensing responses that occurs at the high cell density.
You mean high cell cultivation?
Yeah.
Oh, okay. This is also, so when you come into high viscosity cultivation media, it's also not so easy to mix in the microbioreactor system. So there are limitations.
But even now, but that I wonder in high density cultivation, but without the viscosity problem. I mean, it's just high oxygen demand there. Do you think is
just
still
10,
possible?
10 gram per liter.
Maximum
12 gram per liter. This is the maximum. Yeah.
Okay.
In our case, and now in our experiences, yes. Mm-hmm.
But 10 grams per liter, you can make proteomics and transcriptomics maybe there, no?
But you have
proteomics, but transcriptomics can be done.
Yeah, okay, but you have only this, when you go in the micro reactor scale, then you have 10 microliters. And you can do something with 10 microliters.
Too much.
You need these optical sensor systems.
Okay, thank you very much.
I have some questions about this. Thank you, Rainer, for your talk. You mentioned this phenomenon that is the all-phase behavior that is typical under when the culture get a high viscosity. In your experience, where did you find this kind of phenomenon in the system that you use?
Here? No.
No?
It's more Newtonian broth here. Only when, perhaps because I'm say in resonance and out of resonance. So this is only when you are working in the resonance frequency. Then you have the best oxygen mass transfer at this time. When you're out of this frequency, you are decreasing with your KLA and transport. This is a limitation. So, but viscosity, we have no.
It's close to the water, the viscosity.
Yeah.
Then. Okay. So, and the other question is with respect with this microbioreactor made with 3D printer, because it's interesting. But what is the kind of material that you use it in order to, and especially with the high.
One moment. I will talk also. I have also a talk to the students, a full lecture of this. I have to look. It's not PMMA or something, but we are working together with Janina Bahnemann. She was in former times at the Thomas Scheper Institute at Leipzig, and Leibniz University in Hanover, and she is now professor at the advanced physician in Augsburg, and she had printer systems, and she printed this reactor with our geometries, and we bring together the sensor technique and this reactor technique. So let me look. It's not PMMA or something. It's
another kind.
So and it's also we have to wash out these insides. This is a big manual working step also. In this field.
Good. ¿Más preguntas? ¿No?
Leobardo.
How about the cost? I mean, the whole setup with the sensors and I don't know, because I don't know if the sensors are reusable or are disposable, just the bioreactor. Can you talk about that?
So when you are in research and development, the costs are high. You have to bring it from the scratch on. It needs money for the development, but when you take the material costs and when you know how it works, it's for the parallelization, it's 20 euros or something. But the way to bring it into the company, this is the high prices. The research and development, you can't calculate it in like a business or in a company.
But I mean, do you have any idea that
how much it could cost? In the cent scale.
Okay.
Not the photorun. The glass photorun, when you use the laser technique, it's time consuming. It's better to have polymers or something. It's easier to do this. In the photorun glass, the costs are higher. But you have the good advantages that you have no adsorption of phages at the surfaces, and you have transparent material. You can look what you are cultivated there.
Okay, thank you, Rainer.
¿Alguna otra pregunta? No? So, thank you very much, Rainer, for this
Thank you very
talk.
much.
And